In this video, we're going to learn about acids and bases. You've seen acids and bases in grade 10, and also at the start of grade 11, we did a little bit of review for acids and bases. These are our learning goals. This is a warm-up problem that you should try out before you proceed with this lesson. It's based on the lesson on concentrations. So using your C is equal to N over V calculation, make sure you understand how to do those concepts because they will come back into play when we do some calculations with acids and bases. As usual, there's a great preview the material video that you can watch. It goes over acids, bases, buffers, and a variety of other topics I'll be covering in this last portion of Unit 4. So I do want you to start off reviewing the properties of acids and bases. I would encourage you to make a table in which you compare them. So this video is a great way to do that. You can go back and look at your old notes, but also I would focus on here as well. You can see what is the definition of an acid, what are its major properties, and then how that compares to the definition of a base and its major properties as well. So you would remember things like the taste. For example, acids are sour and bases are bitter. You might remember the texture, like bases feel soapy, whereas acids don't really have a characteristic texture to them. So those are a variety of different examples of properties that you can use to differentiate between acids and bases, and also the word tests that you could use, like litmus paper, indicators that have different colors in acids and bases. And another important characteristic is the pH, which you might remember as well, the pH scale. We'll review that as well, but please make sure that you do make a little note, a little table to compare acids and bases, their similarities and their differences, as well as examples of each. So you can recognize the formula of an acid and recognize the formula of a base. So in grade 11, we learn about acids and bases from two perspectives. There's two theories, or two main theories. There's a few more, but there's two main theories that are used to explain acids and bases. So we have the Arrhenius theory and then the Bronsted-Lowry theory of acids and bases. And so we're going to take a look at how we define acids and bases from the Arrhenius theory point of view, and then also the Bronsted-Lowry point of view. So we'll take a look at both those definitions, how they are similar and also how they are different. So we'll start off with Arrhenius theory. So in the Arrhenius theory, an acid is defined as something that can make H plus in water. In reality, we actually mean H3O plus, but we abbreviate it as H plus. So we don't actually have H plus freely all the time swimming around in water. It exists as H3O plus. So this is actually what it should be, but we abbreviate it as this to make it a bit shorter for us to write. So H plus is actually a hydrogen ion or a proton, but again, when it does exist in the solution, it's going to be as H3O plus, which we call hydronium. So that's the short form for hydronium. So here we can see an acid, HBr, AQ. When you put it in water, it's going to form H3O plus. So the H from the HBr goes to the H2O, that becomes H3O plus, and then you have some Br minus as well swimming around. But that's what makes this an acid. The fact that it increased the concentration of H plus or H3O plus in solution. You can write this as a short form. Rather than put plus H2O, you can just put HBrAQ with an arrow there, put H plus and Br minus. And the fact that we have AQ there really indicates that we have an increase in the H plus concentration happening. Again, in reality, this would be H3O plus, but to shorten it, we put H plus instead. So definition of an acid, something that makes H3O plus or H plus ions in water. It increases the concentration of hydronium in water. A base, on the other hand, is something that will make OH ions in water. So if you look at BaOH2, this will dissociate here to form OH minus and barium plus ions. So the fact that this BaOH2 produced some hydroxide ions in water makes this basic. So acids produce H plus in water, bases produce OH minus ions in water, and that's according to the Arrhenius theory. Now this is a little bit limited. There are some downfalls with this acid-base theory. We'll discuss those downfalls later on, but it is one that we use quite often because it's good enough to explain the idea of acids and bases for now. The main limitations is that in this theory, an acid basically is always an acid. It doesn't matter what solvent you have it in. So if we define HCl as an acid, it needs to be an acid all the time. But in reality, what we've noticed is that substances can act as acids in some solvents and bases in other solvents. So it depends on their environment. So that's one of the problems with the Arrhenius theory, is it doesn't realize that what you act as depends on the solvent that you're in. And so we have to come up with a different theory if this theory can't really explain that. The other thing with the Arrhenius theory is that there are some bases out there that actually do make OH minus ions in water or in a solvent, but they don't contain hydroxides. There's no hydroxide, like ammonia, for example. NH3 is a base, but it doesn't contain hydroxide ions. So Arrhenius' theory could not really explain that. It thought that you have to have OH in a base to be a base, to be considered a base, to make OH minus. But Arrhenius did not realize that, okay, well, this doesn't have OH in it, so why is it that it's making OH ions in solution? So Arrhenius' theory could not really explain that either. And the other thing as well is that Arrhenius' theory of acids and bases only uses water as a solvent, but it doesn't really explain any other solvents when you put substances in them. So it only focuses, it's very limited. This theory is really, as you can see in definition, acids make H plus in water. Bases make OH minus in water. And if something's an acid, it's always an acid, no matter what. It doesn't matter what you're reacting with, it's going to act as an acid. That's according to Arrhenius' theory, but in reality, it's not the case. In bases, they make OH minus ions in water, and so that means they have to have OH. But we've noticed that there are some substances that don't have OH, and they're still basic. They're still somehow producing OH minus ions in water. And then, of course, again, Arrhenius doesn't really explain what happens in other solvents, just focuses on water. So those are the main limitations of the Arrhenius theory. Now we can take a look at the other theory called the Bronsted-Lowry theory of acids and bases. So for a Bronsted-Lowry, an acid, we'll call it BLA, Bronsted-Lowry acid, a blah. It's any compound that can donate a proton, any compound that can kind of give away an H+. And a Bronsted-Lowry base is any compound that accepts a proton. So in other words, it doesn't need to have an OH, it just needs to accept an H+. So let's look at the example over here. Here we have H2O and HCl, and that produced H3O plus and Cl minus. So what that means is that the HCl gave its H to the H2O. So this would be acting as the acid because it donated a proton, a hydrogen, okay? And the H2O would actually be acting as a base because it accepted the hydrogen. It accepted the hydrogen. And so the H2O became a base. There's a double arrow here, and I'll explain that in just a bit. But essentially, briefly, what it means is that this reaction can go back and forth. So donates the H, becomes H3O plus gives back the H. It depends on the situation, of course. It might not go back like this all the time, but that's what a double arrow typically implies. And so we'll go over that in more detail later on. But again, Bronsted-Lowry acids, they donate H's. Bronsted-Lowry bases, they accept H pluses, the protons. So along with this definition, we have other terms to go over. One term is called the conjugate acid-base pairs. So these are two molecules or ions that are related to each other by a transfer of one proton, a single proton, okay? So if we look at this example here we have water and NH3. And so what's going to happen is, here's our products, okay? You'll notice that the NH3 accepted an H to become NH4+. So the NH3 accepted a proton, so that was the base, and the H2O gave away a proton. So the H2O is acting as an acid in this situation. So notice it depends on the context. So it's acting as an acid in this situation. Now, the H2O and the OH minus, they're called conjugate acid-base pairs. The H2O was an acid. It gave away an H and became OH minus. Now the OH minus, if this reaction were to go the other way, the OH minus would accept the proton. And so the OH minus becomes a base. So essentially, if something was an acid, after the reaction, its counterpart is a base. Because if it went the other way, it would be accepting the H instead of giving it away. So this is, waters are acid, and then the hydroxide is a conjugate base of the acid. And over here we have ammonia. It accepted hydrogen, so it was a base. On the other side, its counterpart becomes an acid. It would be its conjugate acid. They're related by one proton, right? So one difference in protons. So notice this is ammonia, this is ammonium, NH4 plus, one extra H, one H less over here, one extra H here. So they are conjugate acid-base pairs. This is a base, this is a conjugate acid. Notice that this would be an acid because if the reaction were to go this way, this would be giving away the H to go to the OH minus. So likewise, if you look at the H2O and the OH, they differ by a single proton. This has one H, this is two H's, this has one H now. And what you may have noticed is that every time a proton's added, you get an extra positive charge. So NH3, when it got a proton, became NH4 plus. And when you lose a proton or you lose a hydrogen plus, you become negative. So H2O lost a hydrogen and became OH minus 1. So every time you gain one proton, you get plus 1, plus 1, plus 1. If you lose a proton, you're minus 1, minus 1, minus 1, minus 1, for as many as you can lose. There's a limit, of course, but that's the idea there. So conjugate acid-base pairs, they're linked. The way they're linked is by one proton being different. If you're a base, your conjugate buddy over here, the acid, becomes an acid. Because if the reaction is going the other way, it would get rid of the H instead of accept. When you're an acid, your conjugate friend over here becomes a base. Because if the reaction was going the other way, it would accept the proton rather than give it away. So you should be able to identify what is acting like an acid, what is acting like a base in a reaction, and then what the conjugate acid and conjugate bases are of the acid and base in that reaction. So here we have just a generic example written out. We have HA and B. So notice that on the other side, we notice that HA lost an H. So HA gave away an H. That means this was our acid. And on the other side, the A minus must be a base, because if the reaction was going this way, this would get an H now instead of giving one away. And notice it became A minus when it lost an H. B received the H from HA. So B, since it accepted a proton, is a base. And its partner on the other side will become an acid. So BH plus is an acid because if it was going the other way, it would give the H to A minus there. And so here we have some examples of conjugate acid-base pairs. So you can see over here we have an acid because the H this is donating the H, and this is our base. Our water is acting as a base in this case because it's accepting an H. And so typically a base will have some lone pairs that it can use to kind of attract the proton with. And then on this side, this would be our conjugate acid, and this would be our conjugate base. So this is, again, just a summary of what we've seen so far. These are Bronsted-Lowry acid-base pairs. You should be able to identify when something's acting as an acid, when something's acting as a base. Notice that it depends on the context. In some contexts, water, for example, can be an acid. Water can be a base. So here we have some more examples of conjugate acid-base pairs. And you should be able to predict what a conjugate acid-base pair would look like. So for example, here I have HNO3, which is nitric acid. This is an acid. If it were to form a conjugate base, well, it would be one proton less. So take away a proton, and you get NO3 and then minus. Here we have H2SO4. And this is sulfuric acid. If you want to get its conjugate base, you remove one proton, so you have HSO4 minus. And then it's the same idea here. Here we have H3O plus. You want to find this conjugate base, remove an H, and you have H2O. And notice we went down one charge, so we're neutral now rather than plus one. And then here we remove an H to get to F minus. Same thing throughout. Okay, so they just differ by one proton. If I ask you to find the conjugate base of an acid, just remove an H, make sure you make it more negative by one, and that's your conjugate base. If I gave you a base and I wanted you to find an acid, a conjugate acid, just add an H and then add a plus every time you add an H to it. So we're going to do a quick example of classifying substances as either Bronsted-Lowry acids, Bronsted-Lowry bases, and then conjugate bases and conjugate acids. Here we have an example. So we have water and ammonia reacting. Notice the water is giving away the H, so the water is going to be our Bronsted-Lowry acid. Its counterpart on the other side is therefore going to be a base, a conjugate base. So this is a Bronsted-Lowry acid. This is its conjugate base. Ammonia received H, so this is going to be our Bronsted-Lowry base. And on the other side, its partner is going to be the conjugate acid of that Bronsted-Lowry base. So you can try to pause the video and try this one out yourself, and then we'll take it up together. So always start looking on the left side. Now I know we have the names there, but that's okay. Look at the difference between this sulfuric acid and this ion over here. This to that side seems like there was an H lost. So that means this gave away an H. Because this gave away an H, this is the Bronsted-Lowry acid, the BLA. So what that basically means is the other thing must be the Bronsted-Lowry base. And it makes sense. If you look, water and its counterpart on the other side, it looks like water gained the proton from the sulfuric acid. So this one accepted a proton. A proton acceptor is a base in Bronsted-Lowry's definition. So water is a Bronsted-Lowry base. The counterpart, the partner here, is going to be the conjugate acid of this Bronsted-Lowry base over here. So that was the example we went over, and there's the answer that we just discussed. One last term to really understand is the concept of amphoteric compounds. So with the definition of Bronsted-Lowry acids and bases, some compounds can act as either acids or bases depending on what reaction you're in. A great example of an amphoteric compound is water. Water can be a base. Water can also be an acid. So if you look at the difference here, here we have water acting as a base. It received an H+. It received an H, so it became H3O+. Here, it gave away an H, so it became OH-. So water would be called an amphoteric compound because it can act as both an acid and a base depending on the reaction that it's going through. And because water can act both as an acid and a base, water can do something quite interesting that we call self-ionization or auto-ionize. Basically, it can react with itself by proton transfer. Within a glass of water, for example, or a sample of water, the waters will transfer protons to each other. So, for example, this water gave a proton to that one there, and now we have H3O+ and OH-. But it's equal amounts, so the H3O+ and OH- would roughly be, would essentially cancel each other out, and you'd have a pH of 7, so the whole solution overall would be considered neutral. But essentially, water self-ionizes, it auto-ionizes. It can react with itself because it can act as both an acid and a base. So this water molecule here was acting as the base, and this water molecule here was acting as an acid within the same sample. And this happens over and over again. It's called proton hopping. Basically, protons jump from one to another, to another, to another, to another, to another, to another. But overall, because it happens equally, it's going to be neutral in the end. So we're going to go and summarize what we just saw about the different definitions of acids and bases, the different theories. And then afterwards, we're gonna watch another video which goes over the strength of acids and bases. So let's go ahead and summarize what we saw here. So remember that I do want you to go over the properties of acids and bases in that introductory video that's in the slide deck. We saw, to explain acids and bases, that there's two main theories. The one you're most familiar with is probably the Arrhenius theory, which is what you would have learned in grade 10. And then afterwards, we saw the Bronsted-Lowry theory. In this table, we compare the Arrhenius and Bronsted-Lowry theory side by side. So when we look at an acid, according to Arrhenius, it's a substance that makes H+ or H3O+ ions in water. And here we have some examples written out. Remember, this is hydronium over here. And if we want to write this as a short form, we'd have HBr will ionize, remember ionize for acids, to form some H+ AQ plus some Br-. So we just took away the H+, and then you become more minus, you become more negative. And so this would be our shortened form of what we saw above over here. Now, according to Bronsted-Lowry, an acid is something that donates a proton. So we look at it more of as a relationship with other substances. So in this situation here, this HCl donated a proton, an H+ to the H2O. So HCl is a Bronsted-Lowry acid because it donated the H+. So again, see that difference. Arrhenius defined an acid as something that makes H+ in water. Whereas Bronsted-Lowry said in some kind of reaction, whatever's donating the H+, that's going to be considered the acid. Now, bases, according to Arrhenius, is anything that makes OH ions, is something that makes OH ions in water. According to Arrhenius, you had to have an OH in your substance to be considered a base because that's all that could theoretically make OH- in water. So here we just see the solid base. You put it in water and it basically dissociates to form OH- and Ba+2. And then you'd balance it, of course, kind of like a dissociation equation you've seen for ionic compounds. But according to Bronsted-Lowry, a BLB, a Bronsted-Lowry base, it's a compound that accepts protons. So here we have water. it accepted a proton from HCl, so that would be considered our base. So this is the H2O would be our base in this situation here because it accepted a proton. How do I know? On the other side, basically your water has one more H than it had before, and it became hydronium. So this is something that increases a proton, that accepts a proton rather than gets rid of one. So we saw that that Arrhenius' theory is very commonly used, but there's a lot of limitations to it. So for example, we saw that according to Arrhenius, an acid should always be an acid no matter what. But we know that's not the case. We know, for example, there are some, so not the case. We know there are substances that can be acid or base depending on the context. We saw water. Example, water is amphoteric. It can be an acid in some contexts and a base in other contexts. Arrhenius couldn't really explain why there are some substances that seem to act as a base. They seem to produce hydroxides, but don't have hydroxides in them. For example, NH3. NH3 acts as a base when you dissolve it in water, but it doesn't contain OH-. And we've seen it in the reaction. We have NH3 plus H2O. Oops, H2O. Let's put our arrows there. Now, generally, when you write this reaction for ammonia, it's a double arrow, and I'll explain why later on. But essentially what happens is the NH3 received an H from the water, and when the water gave away its H, we had some OH- produced. So Arrhenius' theory wasn't good enough to explain essentially why things like that could still be basic but not have OH in them. And it's really because acids and bases is more of a relationship, a proton transfer relationship. And then the other thing is that Arrhenius' theory of acids and bases really only focuses on water as being the solvent, but doesn't explain what happens when you mix other things in there where you have solvents that aren't water. So it wasn't good enough to explain those contexts either. So that's why we now start to go to the Bronsted-Lowry theory of acids and bases, especially when we're looking at chemical reactions and stoichiometry with acids and bases overall. So another thing we saw that came along with the Bronsted-Lowry theory of acids and bases is that of conjugate acid-base pairs. So remember, those are two molecules or ions that are related to each other by the transfer of a single proton. So that's how they're linked. They're linked by the difference of one proton. So we saw the example here. We have HA plus B gives you BH plus and A minus. And so essentially the HA gave away the H to the B. So what happened is the HA would have been the acid, and what it becomes after is a conjugate base. So A minus is the conjugate base to HA. So they would be considered conjugate acid-base pairs. The B is a base because it received H from HA. And on the other side, it becomes BH plus. So B was a base, BH plus is going to be the opposite. BH plus is the conjugate acid of the base B. So BH plus and B would be considered conjugate acid-base pairs. And so you should know how to, this should be liquid, by the way. You should know how to identify conjugate acid-base pairs in examples. So one that we did together was this one over here. So we have sulfuric acid and water, and they produce this bisulfate ion and this hydronium ion. And so what we notice is that the sulfuric acid becomes the bisulfate ion by loss of a proton. So this gave away the H to H2O. So this would be our Bronsted-Lowry acid, or BLA, and the H2SO4 becomes HSO4 minus. This would be our conjugate base, because if you had the acid on the other side, its partner is the base on the right side. Water received the proton, so this is our Bronsted-Lowry base. And on the other side, what is its partner considered? What did it become? It became a conjugate acid. So another term we saw, and I briefly described it above there as well, was the idea of amphoteric. So water is a common amphoteric compound. Basically, what that means is that it can be an acid or base depending on the context. And we also saw that because of that, water can self-ionize or auto-ionize, which basically means it can react with itself. It can transfer protons from one water to another. So here we see, let's just do this example here. Let's say this gives an HOA to that one. So if that happens, we get H3O. When you get an H, you become positive. And then the other one is O minus. And we'd say that's aqueous and aqueous. And that happens back and forth, back and forth, back and forth. So that's why overall a sample of water, even though there's OH minus and H3O plus, is considered a pH of 7 because it's just going back and forth, equal amounts of OH minus and H3O plus being produced. So we'd still be at a pH of 7 overall. So in other words, they're sort of self-neutralizing. They're neutralizing each other. So in this lesson, we saw the acid bases. You're encouraged to make a table that goes over the properties of acids and bases based on that video. So you just compare their similarities and their differences in terms of things like their taste, their pH, what they do to indicators, what they feel like, what they react with, all that stuff there. And then we saw the difference in the definitions and the theories of acids and bases based on Arrhenius and Bronsted-Lowry. We saw why Arrhenius is, it's commonly used, but there are a lot of limitations to it. So sometimes we use Bronsted-Lowry's theory of acids and bases instead, especially when we're studying compounds in different contexts with different relationships and different reactions happening. In the next video, we're going to take a look at the strengths of acids and bases.